Today is the 13th of December, 2014, and this is episode 169. This show is intended for informational and educational purposes only. What cryptocurrency enables is new, empowering, and exciting, but we're not experts, just obsessed companions walking the road towards a more peer-to-peer future.
A couple of weeks ago, Stephanie Murphy and I were sitting down and having a discussion during our host show about an interesting post I saw by Gavin Andresen, chief scientist of the Bitcoin Foundation and core developer, who wrote that he was investigating some interesting technologies, specifically invertible bloom filters, and using those potentially for some optimizations. At that time, I wasn't quite sure what was going on, but it seemed interesting enough, so I put a call out for anyone who had information. And guess who showed up? Gavin Andresen. Hey, Gavin, how's it going?
Hey, Andreas. Good to talk to you. It's going great.
I'm very excited to have you on the show again. As always, it's a pleasure and an honor to have you here to talk to us about the latest in Bitcoin development. So this little project is still in the very early stages, right?
Yes, it is. I'm prototyping and kind of exploring ideas right now. So this won't appear in a Bitcoin software near you for quite a while.
So why don't we start from the beginning? What is the problem that you think this technology potentially could help solve?
So we have a problem right now with miners producing big blocks. And the problem basically boils down to there's an incentive for miners to include fewer translations in their blocks because bigger blocks take longer to propagate across the network than smaller blocks. So as Bitcoin scales up, this is a bad incentive. We want the network to support lots of transactions, but it's expensive for miners to do that. If their blocks take longer to get to other miners, they're more likely to lose what's called a block race. So two miners at different ends of the world can both happen to find a block at about the same time. This happens actually a couple times per day that two miners will find a block within a few seconds to maybe as much as a minute of each other. Then they announce their blocks on opposite sides of the network, and then it takes a while for the network to settle on which block did I see first and which block are we going to build on. Because miners don't want to lose block races, if they lose the block race, they lose that Bitcoin reward and any transaction fees that are in that block. There's this incentive to produce smaller blocks. And so that's the problem that this technology that I'm investigating is designed to solve.
So one thing that's probably not clear to everyone, well, maybe two things. First of all, just finding a block isn't enough. You win by getting that block to as many nodes in the network to accept it as the new greatest difficulty chain before everybody else. So you finding it is great, but then you have to get it out before anybody else gets their block out. So I love the expression, the block race, because it really is a race. And of course, a bigger, fatter block, if you like, that has lots of transactions will move across the network more sluggishly. That's a really interesting point to make. But the second part to that is this is a winner takes all game, right? So you either win the block race and get everything, or you lose the block race and get nothing and have to start from scratch with the next block. There is no second place in this race.
That's exactly right. And in the long run, it doesn't matter. You'll win some block races, you'll lose some block races. It kind of affects everybody the same way. Certainly in the very short run, it's really sad for a miner to see that they solved a block that then gets rejected by the network because somebody on the other side of the world happened to solve it half a second sooner than they did.
We talk often about winning the block race in terms of probabilities, because really that's what it boils down to. But those probabilities, if they're used simply to weight the outcome, don't really reflect reality, because you can't just multiply the probability by 25 Bitcoin, which is the reward, and see what you're going to get, because it's either 0 or 25. It kind of collapses into that. It's in a quantum state, and it collapses into either you got it or you didn't.
Yeah, and it collapses over the course of minutes and possibly even longer. I mean, there can be situations where 49% of the network saw one block first and 51% saw another block. And then you don't know until the following block is solved how the quantum state will collapse. and which one will become the longest chain and which one will be reality.
The current maximum block size is 1 megabyte. However, from casual observation of the blocks that are coming out, we see that that limit is not often reached. Most blocks are smaller than 1 megabyte. The counter pressure essentially is block propagation, and that's why not every block is 1 megabyte. But it seems, at least from what I'm seeing on the network, there isn't a need for big blocks quite yet. This is a problem that we're going to run into as the network scales up in terms of transactions, but not necessarily a problem right now. It's not like transactions are not getting in.
Maybe. It's hard to figure out exactly what's going on because, like almost always, things are complicated. Right now on the network, we have hard-coded transaction fees. The reference implementation transaction fees have been lowered over time, but they've always been hard-coded. Work I did last year was to actually let the fees float, so there's a market for transaction fees based on how quickly transactions are confirming. That kind of distorts the market and distorts what's going on. So I think if we allowed the fees to float, I think that is correct. I think miners would still not create bigger blocks because, they do lose money by losing these block races. I might be wrong about that. That might just be a consequence of kind of the broken market we have right now for transaction fees. And maybe miners would produce larger blocks if there were more transactions because fees were falling, for example. So that's an argument I've heard, that a lot of services that were really big users of the Bitcoin network that were putting out lots of really tiny fee transactions have changed because those hard-coded transaction fees raised, and we imposed things like the dust limit on fees, kind of shut down that use of the blockchain. And so those services have adapted. If we had a completely free market, who knows? I mean, perhaps miners would decide it's fine to allow those kinds of uses. And that's certainly what we're aiming at, is to have a completely free market where miners and people creating transactions kind of interact directly using the fee mechanism to decide, what should appear on the blockchain and what shouldn't.
But right now, the compelling incentive is the block reward. It's about a 250 to 1 ratio between the 25 Bitcoin block reward until 2016 and the maybe 10th of a Bitcoin transactions for a complete block, right? So it's skewed a ratio towards the majority of the incentive. Miners really, really care about reward, and fees are really, really secondary at the moment.
Yes, that's absolutely true. The block subsidy, the 25 Bitcoins they get, completely overwhelms the fees that they get.
So we've identified the problem. The problem is getting more transactions into the block without making the block really big. And how does this technology attempt to solve this problem?
This is a solution that comes from what's known as the set reconciliation literature. I was not aware of until, I think it was Ite pointed out this computer science literature that's an active area of research in distributed networking. Greg Maxwell also kind of pointed me in the right direction. This is all related to what are called error correction codes. And the notion is that if you have two computers that have approximately the same information and they want to kind of reconcile that information so they know, what information do I have that you don't have? And what information do you have that I don't have? There are very efficient algorithms for solving that problem that don't involve sending all of the data back and forth again, and don't even involve like lots of round trips to ask, do you have this piece of data? No, I don't. Maybe you should send it to me. Do you have that piece of data? The invertible Bloom filters, I believe, were invented pretty recently. The papers are all from like 2009, 2010, 2011. So this is kind of a pretty new idea that came out of the academic community. It's really exciting because it's both easy to implement and really incredibly, almost mind-blowingly efficient way of solving this problem. In the context of Bitcoin, what you have is nodes on the network that are creating blocks and sending them to each other. And the blocks that you're likely to create at any point on the network are likely to be pretty similar. So that's kind of one of the key insights, is that if I were to create a block and send it to my peer, it's probably going to look a lot like a block that my peer would create and send to me, because the set of transactions that are waiting to be confirmed is pretty much the same from node to node. I mean, it's not exactly the same, just because you might have heard of some transactions that I haven't heard of yet, or that I decided to ignore, or whatever. But those sets are pretty close to the same. So we can use this set reconciliation algorithm to very efficiently transmit just the differences, the average difference between the block I would create and the block you would create, and save a whole bunch of bandwidth and time.
So to help our listeners understand this, at the moment, set reconciliation is obviously something that's happening. In fact, most desktop computers do it on a variety of protocols for a variety of reasons at the moment. A very common example is BitTorrent, where you have chunks of a file and you're looking for the missing chunks and you try to communicate that information. It's a very inefficient way of doing it, because you simply ask, who has this block, and just found that part of it. And at the moment, Bitcoin works in a very similar way from what I understand, which is that using the inventory protocol message, a node will ask the other node, what do you have? And they'll return back a list of things that they have. And then it will compare with its own inventory and see what it's missing, and then ask for the things that it's missing. So that's very chatty, right?
Yeah, exactly. That's done for transactions. That's done for peers on the network. That's also done for blocks. I'm most interested in the blocks. I'm not proposing changing the way actions are broadcast, although prototyping and kind of exploring this space, I'm guessing we might find other uses for separate reconciliation ideas.
But in this case, what we're talking about is when a transaction goes out onto the network before it's confirmed in its zero confirmation state, it's across the entire network. And in fact, there are a number of services that look at transaction propagation and use that as a proxy to probable or likely confirmation in the future, or tell you how well a transaction is propagating. So by the time you see a block which has confirmed transactions in it, you probably already have maybe 99% of those transactions in your local copy. They've been sitting around in the mempool for a while in pretty much every node. So what you're saying is, rather than sending me, that happens at the moment, the entire block with all of those transactions, which most of those you already have, simply send the differences.
Exactly. The set reconciliation is really kind of mind-blowing, because you're not just sending the differences. In a sense, you're sending all of the data in the block all squished together into a really small form, a little bit of redundant coding. Send that tiny little piece of data across instead of the whole block. And then it doesn't really matter exactly what the differences are. It just matters how many differences are there. Maybe there are, typically 10 transactions that I don't have. You can encode it in such a way that it doesn't matter exactly what those 10 different transactions were. The person you're sending that to can decode the information and reconstruct the entire block if any 10 transactions were different. It doesn't matter exactly what 10 transactions were different. That's really powerful. It's really amazing that it works, but it does work.
This episode of Let's Talk Bitcoin is brought to you by CryptoKit.com, the easiest, fastest way to send Bitcoins right from your browser. That's KryptoKit.com if you'd like to learn more. Today's magic word is scale. That's SCALE, scale. You've got until the 16th of December to visit letstalkbitcoin.com or the Let's Talk Bitcoin iPhone app to enter it for your share of the listener rewards. Back to the show.
So this isn't just identifying what transactions are missing, but what you're saying is reconstructing those transactions from that compressed format without having to ask for them?
Exactly, yes. I mean, you just need to know how many transactions missing or added compared to, what I know. And so kind of network wide, assuming that all peers have roughly the same set of transactions in their memory pools, that should be true because transactions do propagate, they flood across the network. Some will probably get dropped, some maybe haven't made it to you yet, but that number is likely to stay small even as transaction volume goes up. And so since it's just the number of transactions, you can send this kind of compressed chunk to all of your peers. And each one of them, even though they might have a slightly different set of transactions that they're missing, each one of them can construct the full block with just that same piece of data.
So the prototype code you've developed at the moment experiments with invertible Bloom filters. Now, currently a block may be up to a megabyte in size. Have your experiments indicated to any degree what type of size the corresponding or replacement invertible Bloom filter send out? How would that compare to the megabyte size of the block? Are we talking about a 10% reduction? What is the size of the chunk of data that you send?
I don't know yet. That's the short answer. It should be on a 1 megabyte block on the order of, send, how big is an average transaction? Average transaction is 250 bytes. Maybe there are 10 transactions that are missing. That would be a Bloom filter of about 5K to encode those differences. So 5K versus 1 megabyte, is a huge difference. And that depends on, I need to do more experimenting on kind of how synchronized are memory pools. It looks like they're pretty synchronized. So that's good. But then also kind of how much are miners willing to do the same policy for deciding which transactions go blocks. That's another piece of this. I have to be able to assume what block you're likely to be creating. And so there needs to be some agreement on, how are blocks created and what transactions are selected to be put into blocks.
It seems that even beyond the reduction in the size of what you're propagating, the data you're propagating, a secondary benefit here would be that the variance between these propagating chunks of data will be much, much smaller than the variance of blocks based on how many transactions you put in, because transactions will be missing more or less the same, which means that equalizes the race. Is that a correct conclusion?
That is a correct conclusion. I mean, there's even, once we have this technology, then there's an incentive for miners to kind of go along with the other miners are doing. So there's an incentive to create blocks using transactions that the other miners are likely to know about. So I think we'll probably see things like if a miner gets a transaction in their memory pool, they might let it age for 10 or 20 seconds before they actually include it in the blocks that they're creating, just to give it a chance to propagate across the rest of the network. Some people have said that there's an incentive for miners not to propagate transactions, that to keep transactions for themselves, because then they can keep the fees. And this gives the opposite incentive. It's suddenly an incentive for miners to make sure transactions do get propagated across the network. And so that's actually another nice side benefit.
Do you think this will have any impact on consensus attacks, either trying to invalidate block by forking and applying a 51 or some percentage hash power attack? Does this create some kind of change in the incentives or the propagation times, making those attacks easy or less easy?
It needs more thought. I don't think it changes the incentives for a straight up 51% attack. Might have some incentive effects for selfish mining. Although assuming that the selfish miner is still kind of playing along with the rest of the network and kind of creating blocks that look a lot like the blocks that the rest of the network is creating, then I don't think it will have an effect. I think we could do other things that help out with both of those problems. I don't think that this particular change will have much effect.
Philosophically, though, it seems that the algorithm here expresses the idea that matching blocks propagate faster, in that the things that match the majority of everybody else's perspective of what transactions should be included the things that are likely to be closer to the consensus of the selection of transactions will propagate faster than the things that deviate greatly from consensus, which seems like a very nice way to express the goals of the mining algorithm and to strengthen those principles.
It should be kind of censorship resistant also. Is nice, because if miners decide to not include transactions that somebody thinks are bad, but the majority of the network thinks are perfectly okay, then they actually pay a little bit of a price for that. They'll have to create slightly larger bloom filters because they're missing transactions that the rest of the network expects to be there. It kind of works both ways in that it's both transactions that are missing that that your peers expect to be in your blocks, and also additional transactions that peers don't expect to be there, maybe because you didn't send it. So I think it's better all the way around incentive-wise.
Now, let me just clarify one thing. All of this is about network propagation of blocks. This does not affect the storage footprint, if you like, of the blockchain itself. Once this is consumed by a node, presumably, at least at this stage, to have the block stored on disk in exactly the same way as it is today?
Yes. I mean, actually, a roadmap post up at the Bitcoin Foundation blog talks about kind of the short-term scalability problems that we are tackling right now, including storage of blocks on disks. So there's a pull request right now for the reference implementation that implements blockchain pruning so that you only store, the last gigabyte or 400 megabytes or whatever you can afford. So they only store the end of the blockchain and you don't store every single historical block. So in the future, I expect that we will see a good number of archive nodes because this space is cheap. And I think there will always be people who want the whole history of the blockchain disk for whatever reason, either nostalgia or data analysis or whatever. But the vast majority of people will be running pruning nodes that only store enough information to validate the new transactions that are coming in and enough blocks to kind of bootstrap people and give them confidence that they're not being fed an incorrect view of reality. Use a lot fewer resources. So you don't need to dedicate 20, 50, 100 gigabytes of your hard disk to storing the blockchain.
Is this equivalent to making these pruning nodes simplified payment verification, or are you only pruning spent TXO?
They keep the unspent transaction output databases. So it prunes away the old blocks so they can't serve up those blocks to people who might want them. They're still fully validating. So this pull request works. You would download the entire blockchain, the unspent transaction output database, which is sufficient to validate any new transactions that come in, and then prune off the old blocks that are stored on disks because you don't need those anymore. You've already used them to build the list of unspent transaction outputs.
So this is kind of an intermediate node. So you would have essentially archive nodes being very similar to the current full node implementation, pruning nodes being somewhere in between. They've dropped a lot of the already spent transaction outputs and old blocks, and then simplified payments verification where you just have block headers and Merkle.
Exactly, yes.
This is all fascinating stuff. I think I'm generally an optimist when it comes to optimization, in that I think these problems can and will be solved when they become problems. And so a lot of questions, and get a lot of questions when I talk to people. Doesn't this mean that the blockchain is going to collapse when it's adopted broadly? Or aren't we going to be unable to process enough transactions per second? Or all of these doomsday scenarios, which quite honestly, I've heard before. I've heard them for TCP, I've heard them for IP, I've heard them for Ethernet, I've heard them for modems, name the technology, silicon density for chips, graphical processing units. Every single one has dozens of articles predicting the end of the road in terms of performance. And so I dismiss those relatively humbly and say, if that became a problem, there's enough incentive to solve that problem, and there's certainly enough smart people working on it. Do you feel the same way that these get tackled as needed, and there are no significant bottlenecks that worry you as a core developer that seem very difficult to solve at the moment?
Yeah, I do. And maybe that's because we're old, Andreas. Maybe we've just been around long enough. We're all doomed because YZ technology can't possibly scale. Yeah, and I think most people don't realize just how kind of unoptimized all of the code really is yet. It will get optimized. I think a lot of engineers make the mistake of thinking they need to think about scaling to a worldwide scale with billions of robots making gazillions of transactions per second right now. I think if you look at successful technologies, the people who create the successful technologies tend to focus fairly short term. They focus on getting new customers, on making the customers happy, and maybe a little bit in the future in terms of scaling, but they really don't design it to be worldwide scale to start. If you look at Facebook, if you look at Twitter, if you look at even the internet, they all scaled as they went along. And you're right, if you're successful, then you get the resources and the smart people working on it and figuring out how to solve the problems that come up.
I look at it from a technology maturity perspective, and I believe Bitcoin is still in the experimental phase where fragmentation is really an advantage, where trying many different things and experimenting. And you can't do that when you're optimizing. Optimization first requires a lot more standardization. You have to button things down and standardize them in a way that would be inappropriate at this stage of the development, in my mind. But there are differences between making sure the things will ultimate scale versus making sure you don't put anything in there that creates a horrible bottleneck that you're going to come to regret later. Like, for example, getting IP routing tables to scale is a problem right now on the internet, but making IPv4 addresses only 32 bits, well, that kind of could have been maybe predicted. You don't want to introduce a bottleneck like that, or like Y2K, something that will come and bite you just a short decade from now and will be very difficult to change. Other than that, the rest of it can be tackled another day.
Yeah, I mean, certainly looking at kind of things that are theoretically not scalable, that's certainly something that I think about a lot, to make sure that there is some limited set of data that needs to be kept in some computer's memory to validate transactions. That you don't have to trace backwards through, every single transaction to figure out if a transaction is valid. Frankly, some of the ideas people have for building things on the blockchain, they should be thinking harder about some of those problems, because I think some of those ideas just aren't scalable. Invertible
Bloom filters that you're talking about, Gavin, are a new concept relatively recently developed in research and academia outside of Bitcoin. And now you're thinking about how it could be applied to Bitcoin. But Bloom filters, just normal Bloom filters, if you could use that term, are a technology that's existed for quite a bit longer and is already in use within Bitcoin. Can you describe, what the use of Bloom filters is within Bitcoin today?
They're used in two ways, believe it or not. The Level DB database that we use to store the blockchain actually built on top of Bloom filters. That's kind of way down deep inside that database code, very efficiently store data on the disk. We also use Bloom filters for so-called SPV clients, simplified payment verification clients that don't want to look at every single transaction that's going across the network. They can't, because they're a mobile phone that just doesn't have the bandwidth to look at every single transaction going across the network. And even if they did have the bandwidth for the data plan you'd need to hear about every single transaction. So Bloom filters are used for the SPV client to tell a full Bitcoin node, here's a list of the transactions that I'm interested about. But Bloom filters are used so that it's kind of privacy preserving. Bloom filter kind of squashes up all of those addresses that the client is interested in into kind of one opaque blob, where the server can only ask, does this address match this blob? And if it does, it will send it over to the client, and you get a certain, what's called false positive rate. The filter is kind of a fuzzy matching filter where you might get some addresses that you don't actually care about. But that's better for privacy. That way the server doesn't know exactly what addresses you're interested in. It just makes sure that you get the ones you're interested in, maybe a few more.
So a fuzzy search algorithm is probably the easiest way to describe a Bloom filter, asking a question in a kind of vague way so that you get the answer you want among answers that may not match what you want.
Exactly. You'll get either a definite no, definitely not, or you'll get a yes that might not exactly be yes. It might be a yes I don't care about.
Yeah, one of the harder topics to describe and explain, certainly I found that to be the case when I had to write about it, but a fascinating technology, and this new technology of invertible Bloom filters. I've read the papers and I'm still kind of having some difficulty understanding all of it, but it's definitely fascinating technology. This is another thing that I think most people don't realize, especially when you talk to people who are outside of Bitcoin, but even within Bitcoin. The idea, this is not your grandparents' Bitcoin, if you like. This is not 2008 Bitcoin. Bitcoin is constantly evolving. There's a ton of innovation going on. This is not the same Bitcoin that we had 2 years or even a year ago. It's a quite evolved protocol. It's evolved software, and it continues to evolve every single day.
Yeah, that's true. I mean, people ask me, isn't Bitcoin done? What do you do with your day? And I think if you don't work in software, you don't kind of understand the idea of software rot. Unless it's tended, software does rot because things change, the world changes. The big trick is to keep it evolving in the right direction. Make sure we have processes that everybody's happy and comfortable with, because things will change. No matter how much people want things to stay exactly the same, they just can't.
Yeah, until one day the only thing that remains is the name and some of the original design patterns, and everything under the covers has been completely replaced.
No, maybe, I don't know. Old code has a way of living for a very long time. So I think there'll probably still be untouched pieces of Satoshi code in Bitcoin implementations 20, 30, 40, 50 years from now.
Well, I think that certainly has answered all of the questions I had about this little experiment you're doing, the prototyping around invertible Bloom filters. It's great to see some of the practical implications of your roadmap for scalability. And it's very reassuring to see that these things are not only being worked on, but they have practical and in many cases very innovative and interesting solutions that are applying brand new technologies in ways that they haven't been applied before, and are perhaps forging new ground and creating concepts in this space just as fast as people are getting to understand Bitcoin. It's already changing and advancing even further. Thank you so much for explaining these concepts to us.
No problem. Thanks for having me.
Thanks for listening to episode 169 of Let's Talk Bitcoin. Content for today's show was provided by Andreas Antonopoulos and Gavin Andresen. Music was provided for this episode by Jared Rubens and General Fuzz. This episode was edited by Adam B. Levine. See you next time.